Yep, okay. So Lou's got to get things started. Anybody have questions you'd like to ask before we get going? Fired up? Wow, Tuesday afternoon. Okay, Lou, it's your show.
Okay. Today we're gonna cover Lab 6, which is about vector space fundamentals and using the linear algebra to do things like regression. This is today's agenda. We're gonna first cover some of the review of linear independence, and we're gonna learn how to use Null Space to determine linear independence. And we're gonna cover some examples of regression functions to data. So first, we learned this before, how to determine whether a matrix has independent columns by checking those 4 statements. We can see the order columns in the matrix is linear independent equals, we calculate the matrix A transpose plus A, or multiplied A, is invertible. By this, we can check the determinant of this matrix, which is not equals 0. So, and the last one is using LU factorization by checking if the elements in its triangular, in the diagonal of its triangular matrix are non-zero. So in this example, we have a function which called is independent. The input is a matrix, and which this function check if the column vectors in this A matrix are linear independent or not. So this one, we actually use the last statement by checking, by using the LU decomposition. So first, we get the upper triangular matrix U from the LU decomposition, and we calculate the minimum number in its diagonal, and also calculate the absolute value of that value. Then we can say if this value is larger than 0, we return true. If not, returns false. Yeah, this is exactly reflect the last statement to say if there has non-zeros, if the matrix has zeros in its diagonal. Another way to make this more simpler is using the one line, just return, say if this value is approximately equals 0, then we negate this function. It's the same thing as just using the if-else statement. And we can run this, see. This, we can see this matrix is not independent. It means those vectors which are linear dependent. And the first practice, we want to define another function called isIndependent det. By using the statement of determining its determinant of this matrix is 0 or not. And yeah, if it is independent, returns true. If not, returns false. Okay, we'll give a few minutes to finish this function. So basically, we want to see the matrix A transpose multiplied by A is invertible. By determining that, we just calculate the determinant of this matrix to see if the determinant is 0 or not.
Okay, you want to give the solution?
Okay. Yeah, so like several students have the problem, like you compare with exactly the 0. But since the programming has some numerical error, you need to have some kind of tolerance. So for example, in this case, we can first try to say
Should be unhappy, right, if you use a name in the function, det A.
Yeah. And we can compare with 0 if it's larger than, like, give a very small number instead of just 0. Because sometimes when it equals 0, it gives you a very small number. So if this larger than the small number, we think that's not equals 0. We just return true, else to false.
Don't you need to take into account, though, that the determinant might be negative?
The question is, can the determinant be negative? Yes, determinants of matrices can be negative, but it's a special property that we haven't taught you, and Lou and I are cheating. A transpose times A, the determinant is always bigger or equal to 0 because it's a product. So it's called a positive semi-definite matrix. So Lou, we're using a magic incantation that we haven't taught, but life is hard.
You could have done like absolute value around projected K.
I would have done it too. Yeah, if you didn't know that, you could use to add an absolute. Yes, if you didn't know that little fact, you could put an absolute value around the determinant, and then everything would be good. Yeah. So Lou, you could add ABS of this just to be absolutely certain. Yeah.
Okay.
And then we could be fancy. We could go.
Just using.
Put in a comma a tall, and then put in the default here. Yeah. So this is a nice feature of Julia. You can say a tall equals 1 e to the minus 10. And then, oops, copy that. And then that allows you to pass a different value by setting it in the function call. It gives a default to the value of your tolerance.
Why would we want a different value?
Sorry, what's the question?
I was saying, why would we want a different value other than
A different value for a tall? Well, suppose you were working in units of where you have things that are super small, because sometimes 10 to the minus 10 is big if you're looking at roughness on a silicon wafer or something. So maybe your numbers, if you weren't putting them in angstroms, you kept things in meters, and 10 to the minus 10 meters is not very small at all. So it kind of depends on the physics of the problem and what your variables are looking like. Normally, you would try to use better units. So instead of looking at 10 to the minus 10 meters, you would put it in angstroms, which is 10 to the minus 9, and you'd have a tenth of an angstrom. You'd say, okay, that's good.
Yeah, it also depends on the data type you are using. Like if you're using float number, probably use small bytes to describe a number. Then you have the precision is different when you use different data type. And we can also use this function here to replace the if and else. Just returns and give the, it's the same thing as we use the if and else. I can go. Okay. Okay, it should be a float number.
Hey, Lou, let's just move on. That should work, but we can post later. It looks pretty good to me.
Okay. Okay, the practice two is we've learned how to determine the column vectors in a matrix if they are linearly independent or not. Now, if just giving you a set of vectors, how define, like using the function defined before to check if those vectors are linearly independent. Yeah.
While you're using your function that works perfectly, Lou and I will figure out why that one doesn't work, because it should, okay?
I think you need to do HL that was HL.
Should be the same as the minimum of diagonal of u.
Oh yeah, should like this, I think, because that's the defined. Is it?
Yep.
Okay. Okay.
It was this close, okay? It was this close, but that's a problem with computers. Who caught that? Was it Audrey or Emily or somebody back there? Or... Anyway, thank you.
Yes, since this is very simple, we can just give the answer here. So basically, we need to form the matrix A using those vectors. So as we can say, they are already column vectors, so we can. Yeah, we form the matrix A using those vectors, and we just use the function we defined. And it's independent. Those vectors are independent. Okay, any questions so far? Yeah.
I think normally when we do it, don't we usually make them like columns in a big matrix? As opposed to like rows? Because like under that implementation, won't that I don't even know. Won't that be like all rows? Because like they're A1, A2, and A3 are all row vectors.
Yeah, this function only works when they are column vector. If you have row vector, you need to do a transpose first.
Right, so what you did like in the practice 2, like those are all, oh, there's commas.
Yeah, those are column vectors.
Julia, commas are like semicolons in MATLAB, okay? That's, yeah, spaces to make them into row vectors. Yeah, so in MATLAB, that looks like a row vector. Definitely know where you're coming from.
Okay. Example 2 is about another way to check if the vectors are linearly independent or not by using the Null Space. And I think Mani taught this in the lecture, so just briefly review the definition of Null Space. So consider a set of vectors, Vi to Vm, which is n-dimensional vectors. And we form a matrix A using those column vectors. The Null Space of A is defined as this. The X is equals, X is a m-dimensional number, and it such that the A multiplied by X equals a 0 vector. And all this kind of X forms this Null Space. So we can say if we have a X belongs to the Null Space of matrix A, and we have the none or 0x, which means we can have some x not equals to 0. Then by definition, we know those set of vectors are linearly dependent because they need to, the x need to be all 0. Then those vectors are linearly independent. So in this way, we can determine if those set of vectors are linearly dependent or not by checking if they have a non all 0 vectors in the Null space. Is this clear? So basically, what we need to do is we can use a function in Julia to find the Null space of a matrix A. And if this Null space have some vectors which has non-zero element, then we can say those set of vectors is linearly dependent. So first, we're gonna say how to calculate the Null space of a matrix. We need to use in the linear algebra in Julia. And we define a matrix A, and we use this function, Null space, to get the Null space of a matrix A. So as we can see, it gives us like 4x2 matrix, but it is actually, you can see this as a 2-column vectors. So we haven't taught this in the lecture, but those two are actually the orthonormal basis of the Null space of A. It is basis because we have those 2 vectors, and all the linear combination of these 2 vectors are in the Null space of A. So now we can check some properties of this Null space. We get the first column of the Null space matrix V and the second column. And we can show first we can show it is some vector belongs to the null space by plot the A multiplied by those vectors. And second, we show those are orthogonal to each other. This is like the first property of being orthonormal basis. And a second property is the norm of those two vectors equals 1. So we can check this one by one.
Questions on the null space? I mean, Mani covered the fact that if you have a subspace and its dimension is 1 or greater, then it has an infinite number of elements. So how would you want Julia to report all infinite number of elements that belong to the null space? That would be hard, right, to print out an infinite number of vectors in the null space. So what it's doing is giving you two linearly independent vectors in this case that lie in the null space, and all other vectors in the null space are linear combinations of those two. So later, about a week from now, 10 days from now, we'll have a special name. These are called basis vectors because it's the smallest set of vectors you can have that will generate, by doing linear combinations, all of the other vectors that make up the null space. So it's a very powerful computational tool. You're able to represent something that's fundamentally infinite by just giving two elements of it and saying, I can just act on those via linear combinations to build all of the other vectors. Now, this stuff about being orthogonal, later we'll see that means the vectors form a right angle. So if you were doing it in R2 or R3 where you could picture it, you'll see the vectors actually do form a right angle. And we will generalize that notion to being perpendicular or orthogonal. And then the fact that the vectors have length 1, their norm is 1, that's just an arbitrary choice that's very convenient. Julia could return a vector of length pi, e, anything else, but 1 is a very useful, useful value. Okay.
Okay. Any questions on that? Okay. So thus we provide a cleanup function to zero out those small numbers. So we can show those again. We multiply the second column. Maybe.
Yeah, my function may not be working with scalar, Lou, when you do the transpose. That's all.
Okay.
Yeah. I'm a bad programmer. I should have all the cases in there and make sure it's a vector or a matrix.
Okay. Okay, we can say actually here the A multiplied the V1 and V2 all equals 0 vector. And also we can say this V1 and V2 are actually has non-zero numbers, which means the column of A are actually linear dependent. Yeah. So this exercise, we define several vectors, thus V1 to V6, and you are asked to use the null space we just learned, the null space function to determine if they are linearly independent. If they are linearly dependent, calculate the coefficient alpha 1 to alpha m such that the linear combination of this equals 0. Is that clear for the question?
Yeah, cool thing here, if we do the determinant of A transpose A, we can say yes, independent, or no, not independent, and hence dependent, but we don't know the coefficients that will cause a non-trivial linear combination to add up to 0. The null space command is another magic incantation in linear algebra, and it gives you the actual coefficients so that if you add up the columns of A with those coefficients, you will get 0. So that was a question asked in class. How do we find the coefficients such that the combination of vectors adds up to the 0 vector? And this is how you do it. So get to work. Okay, I think people are doing pretty well with this.
Yeah, but I've seen a common misunderstanding is directly make the alpha equals the null space of, say, this vector, this matrix. We can first. So there is a misunderstanding is the alpha is actually just a vector of 6 number, and it is the linear combination of those two vectors in the null space. So what you can do is say, probably change this to A. So alpha should be, so any number, maybe 1 multiply just, and you could choose these scalars, or you just choose either one of those two columns.
Let's try pi times the second column.
This one?
Ooh, yeah, irrational.
Okay.
Oh, it worked. Okay.
Yeah.
So it doesn't even have to be an integer, okay? Just any old number.
Yes. Okay.
Okay, we got 4 minutes to do regression.
Really? Sorry.
Well, that's okay. I just saw the chat, so Lou will get on chat and try to help out there. So this is just getting things set up for linear regression that was covered on class yesterday. So we're going to try to fit a line to data. So we're just going to do y equals mx plus b, but we'll rewrite it as b plus m times x so that we can write it as a row 1x, that's our measured stuff, and then b and m are the unknowns. So guys are used to having x as the unknown, but the unknown can be anything we want. So we want the coefficients. We're going to try to fit a line to data. Okay, and if we end up with like 100 points, we would stack up the 100 measurements, and then this will be a column of 100, and then the x's will be a column of 100 values, but we still have 2 unknowns and we have 2 columns here, so that's the key. The number of unknowns is equal to the number of columns, and this is called the Regressor Matrix, and these are just measured outputs. I don't think it has a special name. Okay, so we'll first just do fitting a line. And if any of my students ever show me data that's this perfect a line, I will know that they never ran the experiment and they just used the random command in MATLAB, okay? Experiments never work that perfectly, but because anybody could just pick out a ruler and draw a pretty good line through that, okay? So how will we do it? We will formulate this problem, and then the least squares solution is you multiply by phi transpose on both sides. If these columns are linearly independent, we know that phi transpose times phi will be invertible, and we'll be able to solve for B and M. And so we're just going to give you the back substitution and forward substitution commands. And so we're going to do exactly that. Y is just all of the measured data. And then a regressor matrix has a column of ones with number of points. So it's one column, and then we put X. And then we're just going to set it up and solve with LU factorization, but with these small matrices, if you did inverse of phi transpose times phi, no one is going to blink now. So now we've got the B vector and the slope. Okay. And if you go back and look at the function that was used in the data, you'll see that these are pretty close. The B was 1 and the slope was 2. And we estimated from our data 0.98 and 1.98, okay? That's pretty darn good. And then we do boop, run, and get the plot. And what do you think? Is that a pretty good line through the data? It's an awesome line through the data, okay? So that's how you do it. Now the thing is, we can fit polynomials, we can do all sorts of crazy things. And so here's a fourth order polynomial. It's got x to the fourth. And we put some noise on the measurements, of course, to pretend that we're running a real experiment. We're doing 100 points again, but we could do 1,000 just as easily. Why not? We'll do 1,000 points, okay? Whoops. Wow, that student worked really hard in the lab. That's a lot of data points, okay? Monty, are your students, they work that hard? Tribby, you don't work that hard? Nobody works that hard, okay? So, and notice how we take a column vector and do powers of it. You do the dot and the caret. That takes every element of the vector and raises it to power 4, the dot and the caret, every element to power 3, etc., okay? Now we want to recover the coefficients. We pretend your trusty high school student doing an internship in your lab now has generated all this data for you, and you want to build a model for it, okay? And we're kind of running out of time here, so I'll help you solve this one really quickly. But even though we know this came from a fourth order polynomial, we'll just write the code so that we can do it with a third order polynomial. And I anticipated us running out of time. Oh, come on. Well, I guess I have to write the code, Lou. Yeah. Anyway, y equals y phi. Yeah, you're right. I can copy some of this example here. Except when you're in a hurry. Oh, I went to the bottom, I went to the bottom, I went to the bottom. Went to the bottom, I went to the bottom. Okay, I'm going to copy this code and just grow the regressor matrix a little bit. Okay, I cheated. It's Lou's code here, not my code. Now we're going to fit this with a cubic. So you see my regressor matrix has a column of 1, so I'll get my estimate is going to be something like a constant plus a coefficient times x, a coefficient times x squared, and a coefficient times x cubed. And See how fast that runs? Now I've got all the coefficients. And there's my fit. Yeah. And you don't have to put these things in order. You could do x to the 7th in here, okay? And this is the hard part when you have data and you don't know what the function is. You have to guess what the basis vectors are. You have to guess. And that's where domain knowledge comes in. If you're working on cars, you might have one set of functions. If you're working on you can even put in sine. So this will take the sine of every entry. Okay? And why should that work? If the cube worked, well, sine of x minus x is approximately x cubed divided by, let's see, 3 factorial. Yeah, so it really looks like a linear combination of x and x squared. But for us, we don't care how crazy the basis vectors are. It's the fact that the unknown coefficients enter linearly in our function. And so I'm going to stop here so that there's plenty of time for the project and stuff, and you guys can take a break. But you can go through and look at the code here. All of it's there for building up a representation of the wave field and fitting to it, okay? So we'll stop here. So take a break, 6 minutes, 5 minutes, and then Triby and Monty, you're up. Okay. Want to bring your laptop up here? Yeah, so I guess if there is a key thing, it's that fitting a line and fitting other crazy functions, it's the same level of difficulty. Exactly the same level of difficulty.
Or it's only like, there's no x, it's not, like you're not raising it to any power, you know that x is always going to be the first power, so like as opposed to guessing what the power is for a.
Yeah, the question is how you start guessing, I think, some of these basis vectors, and in all honesty here, you know, if you want a simple model, there it is, okay? That's a pretty good description of the data right there, okay? Just a straight line. It's not terrible. And then typically you would then go in and play around. I don't know why I would do that. And you see, I didn't improve anything at all. Okay, so you just kind of play around a little bit. But once again, once you've solved the problem once for this particular apparatus, the next time you get data from it, you have a really good idea of how to choose the basis function. So this is what keeps you employed as an engineer. If someone could just hook up MATLAB and give it the data and you don't have to do any kind of work at all about how to choose the basis functions or any kind of domain knowledge, then they don't need you, okay? They can just take somebody off the street to plug in numbers into MATLAB. So this is what keeps us employed. It should be a little mysterious, okay? Just keep it mysterious. Is that wrong, Monty?
Okay, I am going to talk about project 2. I started giving lecture, now I'm taking over everything. You have to see me in recitation, I show up in lab. There's no escape from me. But we are halfway through the semester. So you should be able to download the project file if you go and, ooh, what's going on? I think you can see my screen on Zoom. We can see it in class. So if you go on Canvas and in Files, just like where you found the file for Project 1, now you see a PDF Project 2. This PDF, it's really a supplemental file, so you can read about it, maybe some backgrounds, some introduction, reminding you of the policy of the course. And I am going to use this PDF to describe the project for you. Then after that, Trippi will walk you through the actual files that you deal with. Those ones are through IllumiDesk. You can fetch them. There are 2 files, and Trippi will talk about them. So this project, now if you've done project 1, hopefully you did it. That's a substantial part of your grade. So if you've done project 1, you know how it works. You work on a notebook. We give you some data. You load the data, you solve some problems, and then you submit your assignment. This will be exactly like that. And now the first one, it was about mapping using LiDAR data. This one is, it has a different flavor. It's about regression using an actual data. So there are weather stations across the country. They collect and record data for different things. And this is done by the government, so you can actually access them publicly. It's available for everybody. Last year, we went and downloaded precipitation in Alaska. Why? And we had to download one of them. Probably that looked cleaner, maybe. Why Alaska? Because I think Jesse gave you some reasons. But one reason was that the outline of the state is very interesting. If we choose a state in the middle of the country, you just have to see a square or a rectangle. And we didn't like that. So we thought we want something that has an outline that is more interesting. And Alaska is a very interesting shape on the map. So that's one motivation. So some other people worked on this project last year, Kira and Madhav. You don't see them here. Unfortunately, they're not with us anymore in this course. They're still alive. They're doing well, actually. Both professionally and hopefully personally. What else? Now, this is the actual. This is the actual data or regress data? I think. Yeah.
Using line splines, and that's too fancy for us. But
Yeah.
that's what their data looks like.
Yeah. So they collected data, and data is sparse. You can imagine that you cannot place a station at every single point in the state. Besides not being feasible and expensive, people also would get mad seeing some people recording data wherever they walk, right? That's just not what you want to see. So the government can only have so many employees. So there are some stations very, very far away from each other. But I guess in the northern part or southern part of Ann Arbor, maybe on a rainy day, I think you can imagine they're similar, right? So this spatial sparsity of data is reasonable. It's a good use of resources. Now, what they do, they use something that is more complicated, and you will learn something similar to that in a machine learning course. It's called thin spline, right? It's a spline method. It's an old version of a family of methods that now is called kernel methods in machine learning. Kernel methods were the hyped part of machine learning before deep learning showed up. There were a whole bunch of other people that were famous, and then deep learning took over, and everybody hates the previous people. So we don't know what's the next wave, but generally speaking, all of these algorithms, what they try to do, they try to take data and then find a function that will describe the data for you. That's what they're trying to do. So after doing the regression, and regression is really a mix of interpolation, filling what's missing between your data point, and also extrapolation, a little outside of the data. And extrapolation is usually a harder task. You see all the debates on climate data that what's going to happen 50 years from now. There's so much disagreement because it's mostly extrapolation. It's so hard to estimate and guess what's going to be 50 years from now. So many parameters and things that you need to choose to predict. So a lot of scientists even disagree with them, right? So maybe you can agree on some aspects of it, but generally speaking, models used for extrapolations are, they cannot be very accurate because we cannot predict the future very accurately. That's the problem. But this problem is fine. You're doing mostly interpolation, right? You're filling the gaps. Trippy added some explanations for you why you might want to use regression. You're giving them two examples here. One is, it's the car, right? Yeah. So imagine you want to predict the price of a car, right? You build a company, you have an idea, you launch a website, you ask, come and put your car here, advertise your car, right? And use our market to sell it. Tell me what's the year, if you have an accident, maybe what's the model of the car, what's the brand, what's the color. As many things as you want, right? Now, you can think about these items as these bases. When Jesse was showing you x squared, x to the power of 8, each of these color, year, brand, model, you can think about it as a basis, as a predictor. Now, what they do, they use the data you give. Now, you need enough number of users. So imagine now you have something like 10,000 users. Now, you have a pretty good data set, and maybe you pay and buy some data from other websites and company. Now, all you need to do, you need to fit a model. These days, usually, they use neural networks. Because as you collect more data, it gets better. One problem with older machine learning algorithms was that they would get saturated. At some point, adding more data, it would not increase the performance. But you can do that with neural networks because you can use larger and larger models. So then what they will do, they will build that model, and for a new car that you might not know. So they could use the transactions, right? What was actually the price that market paid for those cars in the past? And then for a new car, they can predict the value of that. Now, there's a company, Zillow, right? It predicts real estate, exactly the same thing. All the transactions, the market, they have the data. They might use your zip code, some neighborhood features, year, renovations, floor type, heating, everything you want, right? When did you change the roof? And they use that, so data is very valuable for them. And they're not going to share their data and model easily with people, right? And what they do regression when your house is not on the market, but you want to track the price, and maybe you want to have an evaluation of it, right? And then they can tell you what's the predicted value of it. In fact, it's publicly available. You can go, but some companies have private products too. It's not publicly available. If you pay, they're paid services. They can give you a more accurate price. Now, that doesn't mean you cannot start a new company because it's very challenging. Like, how do you get all these features and data? If you can come up with better ideas, you can always do better. So regression is everywhere. A lot of apps on your phone, right? They will do these sort of things. Now, typically, we're talking about regression. Broadly speaking, this is part of, now today, it's called supervised learning. That's a fancy name for it. Supervised learning, we have two types of supervised learning. One is classification, the other is regression. Classification, when you're dealing with categories, right? Tell me it's a dog or a cat, right? Regression, you're dealing with continuous outputs. So we are talking about regressions. later, hopefully, you will go take other courses and learn to do classifications too. Classification is very useful as well. A lot of time, we do want to do classifications in reality. So this project is meant to get you familiar. You will be able to solve an actual problem because this is real data, and you are using one of the best tools available, least squares, to solve it. Now, first, you will get your notebooks. In task 1, we are going to use binomial fitting. So this is very similar to what you saw in the lab. That's what you're going to do. The models are linear in coefficients, right? A1, A2, to A4. The basis can be nonlinear. In task 2, we're going to introduce something very different. You are hopefully, after the examples in the lab, you're now convinced that it is very annoying to find the order of the polynomial. Nobody likes to do that, right? And hard to guess. You just need to guess that. Maybe sometimes you can guess it quickly and then solve the problem, and that's fine. But generally speaking, if you have so many features and data is high dimensional, that's not possible. So radial basis functions. These are, let me see if I can draw with my hand. These are bell-shaped curves, right? Like a Gaussian curve. Another name for them is Gaussian basis, but you can also call it radial basis functions, RBF. So these are like bump Gaussian curves, and the idea is that around each data point, let's place a bump like this and use some weights to mix them up. And it turns out you can approximate any function like this. There's a theorem mathematically proved that you can approximate any function like this. But you need probably a lot of them. For example, here we have a function. It's exponential of negative of x times cosine of 2 pi times x. That's the blue curve. We have some noisy samples from that function, and then we only use one. Then we're using one, right? We're only using one basis to have a partial fit. Now you can see that the function is just not capable of covering the whole area measurements because it's only using one basis. So you will need more bases to cover more part. And these bases are local. It's centralized around your data points, these orange dots. You need to choose where you want it to be. Now, suddenly, instead of polynomials, you are, let's say, combining two of these RBF, radial basis functions. You will learn later in machine learning, they call them kernels. And in part B, you're going to use more of them to solve the problem. Now, first, you will need to hand tune because it sounds wonderful until you realize that these bell-shaped curves, they have a hyperparameter. Hyperparameter is a fancy name for a parameter that is not directly parameter of your model. These coefficients, A1, A2, An plus 1, these are parameters of your model. But maybe inside this function f, there is some parameter that you need to tune, right? Then they call them hyperparameters. Because these are not parameters that actually you want to solve for when you solve the least squares problem. So there is a parameter inside this radial basis function f that it affects the quality of outcome. You will need to tune that manually to fit the function. In task 3, finally, you will use this type of function to model the actual data. So first, you will need to do some modification to your previous functions to make it appropriate for the new problem. From one-dimensional, now you're working on a 2D input. Then you need to calculate the weights using least squares, and then finally you need to do inference. Once you solve for the coefficients, you need to run inference to know the values in places that you did not have measurements, right? So you can interpolate. And then you plot the outcome, you should get something like this. Now, this is not going to be perfectly like what they did at NOAA, but it's very similar to that. We are using a more basic algorithm, but it's amazing that least squares is really close to what they do. They use something fancier, which is a link. There's a link here. You can read about it. So that's the introduction on overall what this project is about. And I pass it on to Trippy from here. I'll see you tomorrow in lecture.
Assignments, and then fetch project 2. Now, one thing I've noticed people have missed is that you can access it from here, and then also go in your files and go in the folder, Rob 101, and you should see your assignments here. So after you submit your assignments, a lot of people were accessing, trying to see where your assignments were. You can still see your assignments in the files, right? So we have 2 notebooks for our project, and we suggest that you do them in order. P1, basis functions, it's going to fit the task 1 and task 2, which is just the exponential function that we saw, that we're going to fit on. And then that's working in single basics. It's just an x and a y, right? We saw the plot, and we'll see it again. So the first notebook is P1 basis function. We want you to go over the project PDF in your own time as well. And once you do, I'll solve this one with you. Say your answer is true. And then we will be very happy when we run this. And it just means you read the project PDF and you're aware of what you're doing. So let's pull in our plots and the different packages we're going to need, and try to plot the first data that we have. We also saw in the PDF, it's the exponential function, and we're going to plot the actual data right now, and then from the actual data, because you don't, like our problem is to estimate this function, exponential cosine 2 pi of x. Nobody, if you didn't see it, you wouldn't know what the function is, right? You only have the measurements that you get from your model. You don't actually have the model. So how do we simulate that? We make noisy measurements from that plot. And that's the only information you have, right? So you're going to fit your model based on just the yellow points that you have. And we're suggesting that we use the LU factorization method, and like we solved the least squares in lab also, we convert our least squares into an AX equals B format. And then finally, that's an LU factorization problem, and you're able to do forward substitution followed by backward substitution. So it's very similar to what we'll do in the lab. The functions are also copied from your homework, so you should be familiar with them. And then task 1 is you're just trying to fit a monomial model to your measurements here. So we suggest we're giving you that your basis is going to be cubic, and we ask you to again make predictions on what the y values are going to be. So we're getting a model of y and expressing it in terms of x. Fy is equals f of x, where your function is a monomial function for now. The hat terminology, wherever you see hats, it's usually like the predicted variable. So drawing inferences is always with like variables that have hats on them. That means you're drawing an inference on the model. Then we use the LU factorization pipeline, and we find the coefficients A1, A2, A3, and A4. And then finally, we're able to plot this somewhere around here. We're able to plot this around in this on the same plot that we drew here. I don't have the actual code here, so we're not going to be able to plot it right now. But if you finish the code, you'll see a line that actually fits the data on there. And then one thing that I think students, at least last year, had trouble with is understanding how we calculate goodness of fit. So when you hear the term goodness of fit, it comes from like, I think people in machine learning community use it a lot. But what we're trying to do is, you have, so here's a question. Your goodness of fit is the difference between your predicted variable y and the actual variable y. But you don't, for you, the actual variable is just the measurement, right? So you will get the goodness of fit by comparing. So your measurements have an x and a y, right? And your model that you've calculated just now, it's gonna predict a different value of y called y hat. And your error is y hat minus y, right? That's the. And then finally, we use the norm of that to actually get a goodness of fit for our monomial model. So we're gonna give you the function to do that, and what you will do is you will pass your the coefficients, which is in the A matrix, and your measurements, which is the x value that's going to go in there. So here we get error monomial. This is how you would call the function. You would give it your A that you just calculated, and then the measured x, not the actual x. Is it convincing why we're not using the actual x? Because we don't know it, right? You only know the measurements. And then finally, we plot it for you. And then before we go into task 2, we introduce what radial basis functions are. So a radial basis function has two hyperparameters, which we just learned what hyperparameters are, called x, c, and s, where x, c would be the center of your bases, which is where the bell curve is, so a center where the curve is highest or lowest, and then s, which is the width of that curve. And the function value is the standard, and you'll see it everywhere where they talk about radial basis function. This is how you'll express a function like that. So going ahead and just plotting what a radial basis function looks like. So for x1 equals 0, so the point that I'm calculating, x1, which is the yellow dot, and then xc is where the curve is centered, right? And for now, this is also 0, and then the width of the curve, which is set to 1, so this is probably it goes to like, I think 90% or 80%, I don't know what the cutoff is, where the width is calculated. And then that's where the -1 plus 1 are. So can you predict what happens when I change my x1 to say 2? How would my plot shift? How would it change? Any idea? Yes?
Would the point go up to 2 instead of 1?
Exactly, yeah. So the x1 is the point, like the value that we're getting, right? So it goes down here. And then the value of your basis function is, so maximum value is 1, right? When it was at the center. And then when it's off the center, your value is around, I'm going to guess, 0.2 there, right? Then what happens if I make this 2 also?
It shift over to, like, the entire function would shift over to sector at x is equal to 2.
So your answer is that the whole curve is going to translate, move on to be centered at x equals 2, right? Which is exactly what happens, right? So we know what x1 is going to do, what xc is going to do, and then finally the width. So let's flatten out our curve a little bit, and then it looks more like something like this. If I flatten it more, like 10, it's going to start to look, and if it's like infinity, it's going to start to look like a line, right? So it's, if you were fitting like a linear, like a line that you were trying to fit in the lab examples, you could do that with this also. Although that would be, you don't need to, because it looks like it's a line and you should go for a normal. But you could, if you were trying to be fancy and overkilling. So we get an intuition for what our radial basis functions are. And the next thing we're going to do is we're going to have you hand fit your data, which is the exponential function, right? So we already give you like functions to plot your model, and this function, we'll see a sample call to the function. You're going to give us A0, which is the bias, as they say. So like A0 that you'll tune, hand tune for now, and then A1, which is the coefficient for the F1 function. And then
You're going to hate the hand fitting, okay? You're going to love regression after you try the hand fitting. It is so annoying to choose the hyperparameters and the coefficients and make that thing work. It is going to drive you crazy, so just accept it, right, Tribby? Yeah. Yeah, it's, you just want to hack and do things by hand. That's kind of like, you know, hey, we're engineers, we'll just kind of play with it and make it work. Some of you will get it right off. Took me an hour, okay? I'm terrible at hand fitting. I love regression. It gets it right away.
Yep. Which is why you're going to want to, so wherever you see like hand tuning, we already give you the parameters. So I would say, look at this comment here and ignore the your code comment. So the first thing would be, you're not actually writing any code here. You're only going to be tuning these values, right? So first thing I'll do is I'll remove the error exception. And then we give you some starting values, and let's see how that does. Oh, I didn't click it. We don't have the monomial one yet, so I'm just going to remove that. So our model is so we start with A2 equals 0, so it's a single bell curve, right? So we have a bias, which is the A0, which I'm going to say keep it to 0.05, because that's the best fit that I could find, and I think Professor Grizzle worked for an hour on this, so we got the right values. Don't change the A0. You could, but it just makes it harder to fit properly. Then I would suggest
the curve shows that you have to pay the customer to take your car. It's like if this was the price of the car. You're bleeding cash now by hand tuning. Business is going down.
So the question is how accurate your plot has to be. So we're going to consider it a pass if it produces a total error that is less than 0.5. Right? And right now the error is 11. So it needs a lot of fitting. We do want you to struggle.
Human versus machine.
So the comment is, couldn't we just run the model and come back and adjust the coefficients? 100% you can, yes. But that would just take, I don't think you need to. I would suggest you play around with these values just to get an intuition of what these functions are doing. But yeah, you could very well just run a least squares model, get the values, and you just get the best fit. And we are going to make you do that later, so you could just, you know. But if you were to do hand tuning, the suggested pipeline is that you start with one bell curve, right? So let's try to fit this one. One thing is, so let's fit the first curve, right? I'm going to move this curve all the way here, right? So can you suggest what XC1 should be? What should the center of the curve be? Yeah, look at the plot again. 2? Let's try it. Alright. Let's see. So it kind of brought it in the right alignment, right? The center is more aligned. Now it's just way too far up, right? Which means that the coefficient is too high, right? You're weighting the function too much. So you're getting too big of a value of y. Does that make sense? Right? So your intuition should be, okay, I'm going to adjust A1. Correct? So let's make it like 0.3. Better. Right? Much better. We're nowhere near the first curve, but we're kind of close on the second one, right? Because we're only using one for now. And our fit is significantly better. We're already down to 1.39. So play around with this. I don't want to hand you it in class so that would just be a task done for you. But the suggested pipeline is fit the second curve or fit the first curve first, and then try to fit the other one and play around with your parameters, and then try to find when you have both curves right in place, then I would play around with the width of your kernel. Because the width is going to determine how much these, like, there are two curves, right? If the width is too small, they're not interacting in the middle. If the width is too large, it's a straight line. So you have to find a balance. but that's how I would do it, right?
Yeah, so the key thing to have in mind is you're now going to the state of Alaska. You don't have one dimension, you've got two, and you're going to have like 300 of these functions, okay? Imagine doing that by hand, okay? There's absolutely no physical way that a human being is able to do that, okay? So it's only after playing with it by hand that you understand the power of the mathematics. So that's why we are torturing you. And I had to play with it myself to appreciate how hard these radial basis functions are to work with by hand. But on a computer, they're just gorgeous. They just really are gorgeous.
You do component analysis. So you get like, so for the car pricing model, I plot my price against, let's say, color of the car, right? Then I look at that data and I want to best separate out, I want to see how to best separate out the different prices from the different colored cars, right? So you want to get an intuition of, you don't want to overkill it. Let's say you have 1,000 data points. If you use 1,000 RDL functions, you're just overfitting. You're not getting anything out of it. Any of your predictions are just, they're not going to be very good. So there has to be a balance in how many functions you want to use. So you want that intuition when you're picking up things like that. So, like you suggested, why can't we just train this, right? Why can't we just use least squares and solve it or time fitted? So you're right, and we're going to make you do, the exponential function using the radial basis function, and we give you some functions that you can directly use. So when we're solving it as y hat equals p times alpha, and your job is to find the alpha, what we do is we give you a way to calculate each row of p. So the calc p row function is going to calculate this row right here, okay? Where I equals, say, 1 to however many data points you have. So use the calc p row to get one row of the p matrix. And then finally, you build the full regressor matrix by looping from 1 to n, where n is the number of rows of your p matrix. And then you call that function to build the ith row of your p matrix, and then just assign it to the ith row of your p matrix. And then this function will return the p matrix that you need for RBL functions. And we've already done this for you. So the idea is just that you go over this right in this notebook, and then in the next notebook, you're going to, because it's a surface fit, it's x, y, and z, right? And you're predicting z. So you want to change these functions, calc p row and regressor matrix, to work for 2 dimensions instead of single dimensions. Like we did in project 1. We start with 2 dimensions and then we moved on to the third, and here we start with 1 and then we're moving to the second. Right? But we're giving you code so you have some place to start from. Right? And then we run the least squares pipeline. And then finally, we're just plotting it over here. This should just give you, in the end, we compare your fit from the binomial function and then your fit from the RDF function. And I think the best you will probably tune from your hand-fitted, the best I could get was around like 0.4. And then once you fit it on your RDF function, you're going to get your error down to like 0.44 or something. So it's going to be very impressive, and I'm excited for you to try it. Right? So that would conclude this notebook. which is all about fitting this exponential function and learning how to use RDFs. Now we're going to take this knowledge and we're going to apply it to some real data in trying to fit the precipitation in Alaska. So we read the data, we convert it into a matrix with Julia, and the data is arranged like x values, y values, and then the precipitation value. So your x value is the longitude, your y value is the latitude, and the precipitation is in millimeters. I don't know how to measure it, but I think how much rain occurs. I don't know how much time.
You have boots on the field. They measure the depth of the water. I think you can hang something and then see how much water you collect. That will work too.
So
Does it work in the browser, the link? If you copy the link in the download line, does it work in the browser? Yeah, maybe.
But just copy this portion, or I'll send an updated link, and that should work also. And then just paste it in a new cell, and that should give you the data. Right? For now, I'm just going to upload the data because I haven't uploaded it yet. It should already be there, just don't run that cell. Now make a post about it. If you do run that cell, it'll give you a fix for it. So we read our data from the CSV file, converted it into a matrix, and then we print out the first 5 rows. So the x, which is the longitude, latitude, finally the precipitation. And we sample some rows, so now we're gonna, instead of using the full data set, we give you a function where you can use a percent of the data, and then we are gonna use 1% of our data to actually make the predictions. And let's see, these are gonna be our bases. Finally, this is our bases in 2D, but then we have a better plotting mechanism using GMT. And finally, these are the points that are going to act as your basis vectors, right? Like the centers for your basis vector. And using just these, we're going to be able to predict, like we're going to get the final surface fit that we saw. And that's 1% of our data. So what your task is, first is you want to modify your helper functions. Like we said, the cat free row, so it has throw error exception, you remove that first. So your cat free row and your regressor matrix function will only work for when x is in R1, and now you have to change it to make it work for when x is in R2. It has an x variable and a y variable. You're going to have to make some changes to your code here, run these dummy autograder cells. If you pass them, you're good. Run everything. It's mostly going to be like size errors because we're going from R1 to R2. So as long as you're able to run everything, you're good. And then we have you find your model weights. You calculate A1 to AM, which is your coefficients. Use the LU pipeline, obviously. Finally, do inference. So we give you this news article which says that the rainfall in June, if I'm saying it wrong, was 303 inches or something. You can corroborate that, 370.4 millimeters. And then when you run your model, that's what you should get. And to prove that we're using real data, we're just going to give you that news article so you can be happy about it. And then finally, instead of just doing it at one point, we have you calculated for a grid, which is the grid that we had before, right? The range of longitude and the latitude values. And now you want to make an inference over all of these values. And we give you a for loop. You should write your code here, which predicts the values given that ith longitude and jth latitude. And then finally, we plot it for you. And this plot should be what we saw in the PDF. And that's our project. Make sense? Is it fun? Okay. Sorry about that. Like, it was working pretty good.
We can just test it and give them a new link via Piazza, right?
Yeah, have them just copy this code. Just remove the download and copy everything else because we already give them the CSV file. It was just another thing to download it and replace it. But they already have the files, and they can just read it using.
You should try it locally. Maybe it's pointing to a specific branch of the Git, and
probably.
you have access to it. But
I think it's the token thing. I'll add it to the public Git and then use that link.
okay,
Because the token is probably expiring.
we are out of time. I'm just here to leave the microphone.